You have ridden a bicycle, maybe thousands of times, and physicists as a group could not fully explain why the thing doesn't fall over until the year 2011. Not hadn't gotten around to it, couldn't. For over a century, the textbook answer to why does a moving bicycle stay upright was confidently taught in physics classrooms around the world, demonstrated with spinning wheels in front of students, printed in engineering textbooks as settled fact. And it turned out to be wrong, or at least badly incomplete, disproven by a team of researchers who built a bicycle specifically designed to break the rule and watched it stay upright anyway. By the end of this video, you'll understand the actual history of the bicycle, the textbook explanation for its balance that basically everyone still believes, the experiment that quietly demolished it, and why, on top of being a genuine, unsolved until recently physics puzzle, this same machine turns out to be the single most energy-efficient mode of transportation any species on Earth has ever produced, humans included, unassisted animals included. Physics doesn't dislike the bicycle because it's dangerous or complicated. Physics dislikes the bicycle because it kept being right for 100 years, using an explanation that wasn't actually true. Let's start with where the thing came from, because the bicycle's history is stranger and more recent than most people assume. The earliest real ancestor of the bicycle wasn't a bicycle at all. It had no pedals. In 1817, a German inventor named Karl von Drais built what he called the Laufmaschine, or running machine, a two-wheeled wooden frame you straddled and propelled by pushing your feet directly against the ground, essentially running while seated. It caught on in Europe and America under nicknames like the hobby horse or the dandy horse, and it worked, sort of, but it wasn't remotely close to what you'd recognize as a bike today. Pedals didn't get attached directly to a front wheel until decades later, in the 1860s, creating the machine nicknamed the boneshaker, for exactly the reason you'd guess. Solid iron tires on cobblestone streets, no suspension, no mercy. The real leap, the one that actually gets you to something recognizable, came in 1885 when the English inventor John Kemp Starley introduced the Rover safety bicycle. Before Starley's design, the dominant style was the penny-farthing, with its enormous front wheel and tiny rear wheel. Built that way because a single pedal rotation on a direct drive front wheel could only cover distance proportional to that wheel's size. Bigger wheel, more speed, more distance, but also a genuinely dangerous height to fall from. Starley's breakthrough was a chain-and-sprocket drivetrain connecting the pedals to the rear wheel, which meant both wheels could finally be roughly the same, much smaller size, while gearing did the work that wheel diameter used to do. It was safer, easier to mount, and easier to control, hence the name, and within a decade it had essentially become the template every bicycle since has followed. So the basic shape you're picturing right now has been unchanged, structurally, for well over a century, which makes it even stranger that the actual physics explaining why it works wasn't settled until extremely recently. Here's the textbook explanation you probably heard, whether or not you knew you'd heard it. A moving bicycle stays upright because of gyroscopic precession in the spinning front wheel. Spin a bicycle wheel fast and try to tilt its axis, and it resists, the same way a spinning top resists falling over, or a thrown football wobbles less the faster it spins. Apply that to a leaning bicycle, the theory goes, and the spinning front wheel resists the lean and steers itself back underneath the rider, restoring balance automatically. It's a genuinely satisfying explanation, easy to demonstrate with a spinning bicycle wheel and two hands in front of a classroom, and it's been repeated in textbooks and museum placards for well over 100 years. There's a second classic explanation that usually gets paired with it, called trail. On almost every bicycle, if you extend the steering axis, the imaginary line the fork rotates around, down to the ground, it touches the pavement slightly ahead of where the front tire actually contacts the road. That gap is the trail, and it makes the front wheel behave a little like a caster wheel on a shopping cart. Push a shopping cart, and its wheels naturally swivel to trail behind the direction you're pushing. On a bicycle, trail is supposed to do something similar. If the bike starts to lean and drift off course, The ground pushes back on the front wheel in a way that steers it back into alignment, correcting the fall. Two explanations, both intuitive, both demonstrable, both taught for generations. Both, it turns out, unnecessary. In 2011, a team of researchers, Jody Koosman, Aaron Schwab, and Jim Papadopoulos, working with Cornell professor Andy Ruina, published a paper in the journal Science with a deliberately provocative title: "A bicycle can be self-stable without gyroscopic or caster effects." They didn't just argue this theoretically, they built the bike. Their experimental machine, nicknamed the two-mass skate bicycle, used small counter-rotating wheels specifically engineered to cancel out any gyroscopic spin effect entirely, and its front wheel geometry was adjusted so the trail was actually slightly negative, the exact opposite of the caster effect the old theory required. By the textbook explanation, this bicycle should have been unrideable, or at least completely unable to balance itself. Give it a push and let it roll, and it balanced itself anyway. This is misconception correction number 1, and it's worth sitting with because of just how long it survived unchallenged. The two most commonly cited reasons a bicycle stays upright were both demonstrated, in a controlled experiment, to be entirely optional. What the Cornell-led team found instead was messier and less quotable. Self-stability turns out to emerge from a complicated interaction of multiple design variables at once, especially the position of the front assembly's center of mass relative to the steering axis. When a self-stable bike starts to fall to one side, the front end's weight distribution causes it to steer itself into the fall fast enough to catch itself. The same basic reflex you'd use walking a tightrope, except it's baked entirely into the bicycle's geometry, rather than requiring a rider's brain to do it. Gyroscopic effects and trail can contribute to this in an ordinary bicycle. Neither one, the 2011 experiment proved, is actually required. And here's misconception number 2, which follows directly from the first. This isn't some obscure correction buried in an academic journal that never reached anyone. The old gyroscopic and trail explanation is still what gets taught in plenty of classrooms and repeated in plenty of documentaries today, more than a decade after it was experimentally overturned, simply because it's a better story for a 2-minute demonstration than the interaction of at least half a dozen design parameters in ways we're still mapping out. Being wrong, in this case, was never really the problem. Being simple enough to fit on a whiteboard was the whole appeal. One more layer of nuance worth adding here, because it matters for how you actually think about riding one. That self-stability window only exists for a bicycle rolling within a specific range of speeds, riderless, on its own. Once an actual human is sitting on top of it, which is obviously the normal condition for every bicycle you've ever seen, active balance from the rider's own steering and body corrections is doing a huge amount of the real-time work, especially at low speed, where most bikes aren't in their passively stable range at all. Anyone who's tried to ride at walking pace and felt the handlebars wobble under their own hands has already discovered this personally. The machine's passive stability is real, and it's genuinely useful, but it's not a complete substitute for the rider constantly, unconsciously, making tiny corrections the whole time, much closer to balancing a broom upright on your palm than most people assume. If it took professional physicists and engineers until 2011 to actually nail down why the machine you learned to ride at age 6 doesn't fall over, a like helps a video like this reach more people who'd enjoy finding that out too. Because the balancing act is only half of why this machine deserves the reputation it has. The other half is what happens once it's moving forward. Because pound for pound, calorie for calorie, nothing else humans have ever built, and nothing else evolution has ever built either, moves a body across the ground as efficiently as a bicycle does. In the early 1970s, a comparative physiologist named Vance Tucker at Duke University, alongside a related and widely cited analysis published in Scientific American the same year, set out to compare the energy cost of movement across an enormous range of species and machines, birds, fish, mammals, walking humans, and humans on bicycles, measured in energy spent per unit of body mass, moved per unit of distance. Ranked from most efficient to least, the results were genuinely surprising. Among unassisted animals, the most efficient mover on the planet turned out to be the condor, a bird that can glide for miles on almost no energy expenditure at all. And then, above even the condor, sat a human being on a bicycle. A person walking burns roughly 5 times more energy per unit of distance than that same person riding a bike at a comparable pace. The precise multiplier varies by source, generally cited between 4 and 5 times. Later analyses have repeated the comparison with modern data and kept landing on the same conclusion decades later. Humans, who are honestly kind of mediocre movers on our own 2 feet compared to a lot of the animal kingdom, become one of the most energy-efficient traveling organisms on the planet the moment you put us on 2 wheels. So why? What is the bicycle actually doing differently? 2 things, mainly, and they both come down to physics the machine handles, so you don't have to. The first is gravity. Every single stride you take while walking or running involves your body's center of mass, rising and falling slightly with each step. You are, quite literally, hopping your own body weight upward against gravity over and over, thousands of times per mile, and every inch of that vertical motion costs energy that does absolutely nothing to move you forward. A rigid bicycle frame on 2 wheels eliminates almost all of that vertical bounce. Your body glides in a smooth, mostly horizontal line instead of a repeated series of tiny leaps, and gravity simply stops being an opponent you're fighting with every single step. The second is the drivetrain itself, the same chain and sprocket system John Kemp Starley popularized back in 1885, refined over a century into something that converts the force from your legs into forward motion with remarkably little wasted energy, commonly cited at somewhere north of 90% mechanical efficiency. The exact drivetrain efficiency figures vary by source and by drivetrain condition. Compare that to a car engine, which loses the overwhelming majority of the energy locked in its fuel to heat before a single watt ever reaches the wheels, or to your own muscles walking, which are burning a huge fraction of every calorie just to keep your body upright and swinging your limbs through the air. On a bike, almost every unit of energy your legs produce goes into one job: pushing the wheels forward. And once you're moving, the wheels themselves keep you coasting on stored momentum between pedal strokes, which walking simply cannot do. Every stride starts from a near total stop. Nobody has fully solved the bicycle. It stays upright through a mechanism that took professionals over a century to actually pin down, and it moves a human body through space more efficiently than a condor's wings, more efficiently than a fish's fins, more efficiently than anything with a combustion engine bolted to it. And it does both of those things using a design that hasn't fundamentally changed since 1885. If a machine you've ridden without a second thought turns out to be one of the least fully understood pieces of everyday engineering on the planet, hit subscribe, drop a like if any part of this genuinely surprised you, and tell me in the comments what other, obviously simple object you'd want unpacked like this next. One last thing, and it's a physics fact hiding in plain sight every single time you've ever turned a bicycle. To steer right, you first, very briefly, turn the handlebars left. It's called countersteering. It applies to every 2-wheeled vehicle from bicycles to motorcycles, and almost nobody who does it correctly every single time they ride is consciously aware they're doing it. Turning the handlebars slightly left first causes the bike to lean to the right. Remember, leaning is what actually initiates a turn on 2 wheels, not the direction the wheel points. And once it's leaning, the bike carries itself through the right-hand turn. Try to steer directly into a turn without that initial, tiny opposite twitch at any real speed, and the bike resists you instead of turning. Every experienced cyclist and motorcyclist on Earth does this automatically, thousands of times a ride, and the overwhelming majority of them have never once noticed they're doing the opposite of what their hands feel like they're doing.